Can you see my screen okay?
Yes, I can see the screen. Yep.
So hello everyone, and it is my great pleasure to have this opportunity to share with some of my work, probably in the last 10 years. As Hiram said, my background is on solidification, or has been on solidification, but with its application into casting, welding, and additive manufacturing, right? Today, probably more just focus on welding of steels, and then so I said I'm talking to the audience from WMG Steel Group. I think they're probably the largest group in the country. So I'll start with probably kind of fluid flow, and then followed by second part will be on solidification in the med pool during arc welding of steel, right? A majority of work actually came from a European project, something called weld. Sounds like chocolate name, but it's a consortium we made up of different, 7 different groups, and look into multi-scale, multi-physics modeling of welding, right? So I really need to acknowledge the weld project. So Karen told me you have probably a little bit quite diverse background. I gave you 2 slides to introduce the welding. So welding is important. It's an important manufacturing route. And if you look around, about 50% of global domestic or your engineering products contain weld joints. So it also supports a diverse sector of companies according to very different sectors. Look into the picture showing automotive, and then look into pipeline or gas and oil platforms, shipbuilding, construction, aerospace, defense. So welding has been actually quite dynamic topic in this kind of metal processing area. So what it looks like, welding is a permanent metallic joint. You have 2 pieces of metals that can be the same and or can be different. If the same, we call it similar welding. If it's different, it's called dissimilar welding, right? After you met those we said joints, and then you after solidification will form kind of a permanent metallic joints. So that's called a welding process, and is by forming these permanent joints between these 2 parts. So what really happens? For example, if you look at it's one of the most popular welding method we call arc welding, right? So you have 2 different, we call workpiece A and B in the bottom. Now we put them together and want to form a permanent joint between those 2 parts. And then you will have kind of something like called arc gun, or can be laser gun as well. But if it's arc gun, the arc gun will act as cathode over there, and then this metal piece will be allowed over there. So when those 2 getting close enough, and you form kind of arc, and this is called arc will form in this area. Normally it's plasma gas area over there. It can be very hot. The temperature can easily get to 2000, over 2000, 2600 degrees C, right? So what will happen then? You melt those filler materials in this area, and then will be completely mixed. And we'll look into how fast it is in this weld pool. We call it internal flow inside the weld pool. And then we're followed by solidification. And the solidification look into, you always grow from this kind of solid liquid interface, grows towards this center of the weld joints. So this we say to us, we say welding has these 3 phenomena: melting, mixing, and solidify, right? So we develop kind of modeling framework. We say this welding is kind of multiple physics and multiple scale phenomena. So if you look into it in more detail, look into processing, look into chemistry and structural correlation in welding. So we build this kind of we call a framework of modeling activities for welding. So on the top one, we mainly address chemistry issue, right? And in the bottom side, we look into processing wise, look into heat, thermal, flow, and stress issues. On the right hand side, this would be we can performance, look into structure integrity and cracking, and look into hot cracking or cold cracking. And cold cracking normally when mentioned to the hydrogen embrittlement. So I think the most important thing we did in this work, we established data flow and at different scales of modeling, right? If we start from chemistry side, look into really want a very small scale, quantum scale. The tools would be models would be ab initio and quantum mechanic. At this scale, probably you will get kind of a thermodynamic data. This is really thermodynamic. You look into electron interactions and it's at atomic scale thermodynamics. And also you can probably be able to solve the force field between different atoms. We did try to do this kind of interaction between hydrogen and alloy. We tried, but we didn't get anything out of it. Yeah, but this is still quite hot area. Looking to hydrogen embrittlement in metals. We're still continuing our effort, but there are many unknown things in there. But from there, you also can look at the interface properties and interatomic potentials. And those, in particular, those interatomic potential will be required by this kind of a larger scale, look into probably millions of atoms. We can molecular dynamic scale, right? So from this scale, and then you look into probably at millions of atoms, and then you can look into hydrogen diffusion, and then, or you can look at cohesive zone models and correlate this into mechanic performance as well, right? So if we move down to a little bit larger scale, we say you got millions of atoms, and you can move on to the micro scale level, look into, for example, you can use phase field modeling or phase field crystal modeling. But this MD model will be able to give you data. We say those are data are leaded between those two labeling models. Look into interface structures, look into thermodynamic property of solid, liquid, or solid interfaces. And then those also, the signal will flow backwards as well. From phase field, probably you'll be able to provide chemical. Can you hear me now? Right, I see a signal come up, right? So so if I look further down, look into processing side.
Somehow we can't hear you. You're in the mute.
Yeah, someone has been keep on unmuting me. I'm not sure what happened to it.
Oh, okay. Okay, I can hear you. Yeah.
Can you hear me now?
Yeah, I can hear you.
Right. Okay. Yeah. So if we from the bottom side look into processing wise, look into heat flow, we can say look into boundary conditions, solidification fronts, and the matches on permeability. And this is normally looking at FE tools to analyze them. And then followed by kind of a grain structure level, look into chromal grain, equax grain, and then you get the dendritic kinetics, solidification interface, and the microscopic properties over there, right? So those we said welding is kind of a multi-phase, scale phenomena, but we probably be just able to flow the data between those different labeling scales, right? And in the end, and all this kind of chemistry from top, processing from the bottom, we have an inference on this microstructure, look at the microscale phases, also microscale defects, right? So you can get a microstructure, chemistry, thermodynamics, look into also fractures or defect growth and residual stress, those sort of level. And this will be linked with kind of a smaller scale kind of diffusion of hydrogen and cohesive zone model to give information for you to predict mechanical performance, such as structure integrity, or hot cracking or cold crackings. So this is the overall structure, and it's 4 years work. And today, probably our focus on two things. First on, we try to look into flow, or identify internal flow within the arc welding, and then look into solidification, those two phenomena. Right. So first part will be fluid flow in the metal pool, right? First, we look at the forces acting on the weld pool during welding or during arc welding. So you will look into analyze those actual forces on it. We will look into first one with Maragori force, essentially the surface force, and then we'll look into a little bit more detail and why it's important. And then second force, you have arc drag force, which is normally acting on the surface as well. And this is normally it's arc pulling force, actually a drag force. And you will have a buoyant force and a Lorentz force. Buoyant force is density difference, and Lorentz force because electromagnetic effect, right? But those forces have different kind of functions. Some of them will be able to, we can widen the pool, and some of them will deepening the pool. But those is important because this will affect the welding performance. And also, if you look now that we look into additive manufacturing using arc wire method, and then this also affects the formability. Actually, you want to control the morphology of bead. You have ways by controlling those different forces. For example, we will give you an example later on. Look into this Maragori force change, surface force change, and can we modify surface and to modify the morphology of the weld bead, and also look into formability of the additive manufacturing using arc weld method. So if we group them, say those forces, when Maragori force, when your surface tension against temperature change is less than is elective, so you will have kind of widened force, and arc drag force always is actually to pull the your pool, widen it, and similar to the buoyant force, this is the force acting internally or either on the surface or internally in the metal pool. Deepening the pool, look into many Maragori force when you got surface tension increase as temperature increases, or Lorentz force again it's try to deepen the pool, right? So now look into kind of we say importance of these different forces. Generally speaking, we do not have accurate data. We try to measure it, it has been very difficult. Those are the probably the rule of thumb look into. So we probably look into first from Maragori force, and then you look into probably 10 minus 4-ish, and then similar level to arc drag force. And Lorentz force is 1 magnitude lower. Buoyant force is even lower, depending on. Anyway, this will depend on materials. The rule of thumb, you probably have this kind of ratio of power, or ratio of the force acting on your weld pool. Arc drag force probably in the same order of Maragori force, and then Lorentz force is 1 magnitude less, and buoyant force is probably 2 magnitude less, right? So those are the main forces acting on the weld pool, and then so how to characterize them, right? If you look probably 10 years ago, we normally look at ex situ method, and you can examine this kind of metallography of we as other solidified metals try to trace out, but this is the indirect method. And then at early days, and then use a laser beam to look at surface phenomena. And then you will not be able to see the internal flow. But internal flow can be different, very different with the surface flows, right? And then people try to use organic materials, and then you are limited to the analog systems, right? Since X-ray has come in probably since the 1970s, and people start to use X-ray to look into internal or look through liquid matter, and then try to figure out what happened during welding, right? This we said electromagnetic spectrum, and X-ray gave us opportunity. Actually, you can see through the matters. to a certain length of your material. So to observe kind of kinetic or this kind of very dynamic process, transmission method, image method is one of the popular method. And generally speaking, it's X-ray or attenuation, and when X-ray trans through your material, right? And then we said transmission will be lost when X-ray penetrating through either steel or liquid solid steel or other metals, right? And then we something called attenuation in X-ray, but generally speaking, and this will depend on your output and input correlation, and then this will depend on your materials. So will depend on what kind of materials it is, and then density of materials is also another concern, and then grading angles. And normally, it is where or how the X-ray acting on your sample, right? So by considering this into account, and then you probably can choose what kind of X-ray you can use. For example, if we want to do any steel study, and this is a figure probably you come across before, and then you will see enough difference and give you enough attenuation length, look into 10 millimeters, and then you really need to get this kind of energy level. But again, which energy we use and depends on what purpose you want to see it, right? So after you probably have done this kind of basic kind of calculation, and then you should really talk to a beamline scientist and to look at what kind of imaging method you want to use. You have radiography, is essentially transmission, and tomography or topographic. Those techniques you want to use, and then probably if you look at this synchrotron X-ray radiography, and then essentially it's transmission image. It's 2D, it's direct. And now they can get spatial resolution. Nowadays they can get micrometers if you push to the limit. And then the temporal resolution can be 0.1 or even 0.1 milliseconds, right? Because we have very fast detecting system which can accommodate the higher spatial resolution, right? And then you have good dynamic absorption and also got refraction constants. You need to consider. You can look into, or you can examine, we get solid liquid interface, and you can look solid boundaries, probably just be able to see it, and then you will be able to hydrodynamics in this liquid, right? There are probably many groups now in the world that using this method to look into it. And nowadays, you also can have probably look into ultra-fast methods, and then essentially you will get probably much finer kinetics because you can do the faster sampling rate, and you can look into this from the hot tearing, porosity formation, even precipitates can be studied as using this ultra-fast synchrotron X-ray tomography. So in our experiments, and we did this kind of design. It's quite simple, and then so this is our arc gun, right? And then we got beam source comes through this way, and this is detector, essentially transmission detector. And we try to cool down sort of copper block. And at the initial design, we want to actually rotate the sample, but in the end we gave up because of the dynamic in the weld pool is much faster than the rotating speed you can achieve. Right. So this is what it looks like. This our sample sitting in there, and this X-ray pass over there, and then this is surrounding area. Make sure this liquid will not be splashed out, right? And we tried per 100 keV as I showed earlier. We want to see probably as many photos as possible. We use a white beam model, and then probably at that time we got 13 kind of micrometers pixel resolution what we can get, and we can get 1,000 frames per second as captured. We did also try 2,000 seconds as well. Right? In this experiments, and then we also use particles. Use particles to trace the internal flow. The particles we choose, we use tungsten and tantalum. Particle we added to, but in the end, we select tungsten. Tungsten can stay longer time in the weld pool compared with tantalum. Right? So this is a bit of a kind of conventional welding parameters you want to use, and then this is a bit of summary. We use tungsten particle, and we use high beam energy and high frame rate in this radiographic imaging. We tried this kind of CCOMS kind of detect camera, and many want to gain this spatial resolution and also temporal resolution as well. Right. Yeah, imaging processing is another way. After doing experiment, and the process image is important. First one, we said we should differentiate image method, and we run experiment without welding and with welding, and then it takes differential signal from each other, and which will give you this phenomena which happens inside the area you are interested in. For example, when you want to see the signal within the med pool. Right? So this is probably a little bit mathematics to tell you, and this again it depends if you have particles into your weld pool, and those particles and we are probably absorb a little bit more kind of X-ray. So this gives us a signal and to trace the internal flow streams. So this is our experiments, and this is what looks like. I think this the overall the length is about 10 millimeters. This view window is about 10 millimeters, so 10 millimeters. Now you should be able to see the arc gun in the top, and then you have this kind of, we call it free surface of the liquid matter moving up and down. After the melting the pool, this will be melt pool, you see those black particles inside. These black particles are tungsten particles. Because tungsten particles absorb a little bit more X-ray, so you will see it a bit dark-ish. So this is the raw image. After we get this raw image, and then we use image processing method to trace the individual particles over each frame, right? And those actually the tracing took us probably more than half a year to figure out and how to this tracing individual particles inside of the pool, and then work out the average speed or the maximum speed of this kind of internal flow streams. Now, this is the way we want to trace in the particles. So we got tungsten, it should be tungsten particles in there inside the liquid pool, and we're not tracing the paths, individual paths. By doing this, and we'll be able to see the individual flow stream inside the weld pool. Probably you may argue, and this is a 2D projection of 3D phenomena. We tried very hard actually. Try to get 3D. We tried to use better 2D image to walk backwards into 3D. I think it has been proved impossible. In the future, I think we should really want to use essentially two synchrotron X-ray beam, two detectors, and then you view this phenomena from different angle. And with those two kind of new setup, you'll be able to construct into 3D. But here we only got 2D imaging. But we say probably this will be okay if you analyze 10 or 20 of them, and then you will probably have a chance to look into the stream path, probably just at the right angle of the screen. So this, at least the maximum speed we get, it should be the right ones, right? So we said now when we have a chance to look into internal flow, so what do we really want to study into it? And then we said probably look into one phenomenon we want to see the internal flow stream, what it looks like. And then we also get the average speed and also maximum speed of the internal stream. This is important, and then we still think we are the first group actually to did this measurement for the welding of steel. So those will be available to do any to validate your modeling, and then probably all help you to design the welding process, right? So now in the next few slides, I will look into how this kind of a surface tension change and can modify the internal flow, and then modify the morphology of the weld pool shape. Example, we said, you know, this is previous study say sapphire can be act as a surface active agent to reduce the surface tensions, and then you can see the when you got low sapphire and you got higher space tension, you got very quite shallow pools. When you introduce probably this kind of sapphire surface acting agent, and then you can deepen the pool and modify the morphology of the weld pool significantly, right? Now we look into two kind of level of sapphires in our study. Start with left-hand side is the lower one, and the right-hand side is higher concentration. It's very high this way anyway, but we want to see this actual effect. But this transition point should be very low between those two, but we choose those two. This is quite arbitrary level of sapphire, but we want to demonstrate the effect of a surface tension change on the weld pool. So those are, if you look at this time resolving image, look into 500 milliseconds, and then to 1000 milliseconds to 2000 milliseconds, analyze the shape, mainly look into width and the depth at different time to see this morphology evolution. And also you will see this average speed of these particles. And then look, average one will be 0.08, the maximum one will be 0.31 meters per second. The average one has sometimes it's probably has not very accurate because 2D projection of 3D phenomena. The maximum speed we are quite confident should be a quite accurate estimation, right? And then you can see and how this morphology changes from this kind of wide, shallow one into this kind of deep pools. And this probably would be direct evidence to see how the internal flow to modify morphology of the pool. And also this will say speed, maximum speed is about 0.5 meters per second. This is very significant. If you look at your pool size, normally for say the pool from there to there is about 10 millimeters in diameter. So 10 millimeter diameter in this very small tiny pool, and you got flow inside which flows at 0.5 meters per second. So roughly, if you look into it, so how many revolutions will you have per second? So probably look into if diameter times pi, and that would be if diameter is 10 millimeters times 3.4, that would be 30-ish, and divide by this 0.5 meters per second. So roughly probably 50-ish kind of full rotation inside. So those kind of flow rotate very fast. So, and then when we design experiments, the rotating does not have any effect because your dynamics is much faster than this actually a sample you can rotate at. So probably this is a quick summary of this fluid flow in welding. We said weld fluid flow in steel now has been observed in situ. When we did experiment, we were the first group did that. Actually, yeah. And then flow velocity can be has been characterized at speeds of up to 0.52 meters per second. It's very dynamic formula in the weld pool. And then surface active agent sapphire has an important role in creating welding geometry. And also, if you look at additive manufacturing wise, if you look arc welding, arc wire additive manufacturing, and you should really think design some surface active agents to modify the geometry, and it will significantly affect the formability of your additive manufacturing route. With a high sulfur content, reduce surface tension and push warm molten matter to the bottom of the weld, therefore increase the depth or increase the penetration, and you have much deeper weld pool or weld bead. And the low sulfur ones and many increase surface tension and then pull the warm liquid matter to the edges of your weld pool and result in a wide and shallow welding bead welding pools. So now I move on to the second part of my talk, look into solidification. Now we got liquid metal and has been fully mixed, and solidification will cool down. Fully solidification will occur. Today I will talk solidification more, a lot solid state transformation, but look into how liquid transform to solid, right? This will be, we say, look in the grain structure level, and normally we'll look at the very fine grains around the interfaces, right? And then around this interface, and in the center one, and then you will have some columnar equal grain will grow, and normally in the center one you have some equal X grains to form. So today I probably want to do some fundamental studies, look into how this grain structure changes now from this kind of very small fine grains to columnar grains and then to equal X grains, right? So something called columnar to equal X transition. This not only happens in welding, or also happens in casting, and in most solidification conditions, you have probably columnar grains and normally elongated longer ones, or equal X one, you can round the shape and grains. So how this transition occurs, this has been topic for a long time in solidification study. So we try to gain a bit deeper by doing probably we call a structure, a solute-driven solidification modeling to look into how this kind of grain structure can be changed, or you can control grain structure to either columnar or either equal X grains. This probably it's a well-established theory looking to effect velocity on this scale, and then thermal gradient on the horizontal axis. So this we call it with a CET map. If you processing condition in this kind of area and you grow equal X grain, and if you at this kind of level, then essentially you either have so high thermal gradient, low growing velocity, you form these columnar grains. So this is the earlier kind of studies using analytical way to analyze them. And today I will show you using computer simulation method to simulate this kind of transition from columnar to equal X transitions. Yeah, we use something called a solute blocking approach. Many this would be a dendrite solid phase, and this will be liquid phase. For example, we grow dendrites from left hand side to the right hand side, and then see at the solidification interface. And because most alloys and have alloy components, and normally we use a partition coefficient less than 1. For example, aluminum copper, nickel aluminum, iron carbon systems, and they all have alloy elements which have partition coefficient less than 1. So you got kind of enriched kind of layer of solid elements, and how this actually can affect solidification morphologies, right? So we use this kind of solute blocking approach, and then now look at we said equilibrium condition at solidification interface, and this is a schematic diagram of binary phase for partition coefficient element for element with partition coefficient less than 1. This applies to aluminum copper, nickel aluminum, iron carbon systems, right? Now we can, for example, and you have this is called liquid line, and this is called solid line. You cool down from liquid to solid, and then can we control? How can we control the morphology of the solidified structures, right? So I think in most modeling, as in nowadays, whatever tool you use, and we probably assume a local equilibrium at solidification interface. means at the solidification interface, and then your chemistry of solid phase, which is we call it would be at the end of tie lines here, and the chemistry of liquid phase is determined by thermodynamic equilibrium states, and then those are fixed, right? And then kinetics may play a role, but kinetics play look into diffusion wise. But for modeling, solidification modeling, and we in most modeling case, and we use local equilibrium condition. Right. And also, which means interface temperature is pretty fixed. And look into this interface temperature. Essentially, so we can start with this one. We start from F or Tm should be, and then times the distance of those two essentially is the slope times the concentration difference, and take away those two terms. Then those two terms, the first term is curvature. The curvature always plays a role, and curvature in particular when looking at Coulson effect, and it's important. And delta TK is kinetic and normally you can ignore it, and it's probably 1 or 2 magnitude lower than those two, and this also probably is 1 or 2 magnitude than this undercooling. So when we grow crystals, for example, we grow a crystal, what will happening? And essentially this will be control equation, and this is because you have a solid liquid have different chemistry, and you grow at this velocity. And those are chemistry concentration different. Essentially, those solid atoms will be pushed into the liquid from interface. Those amount of solid element will be pushed towards into the liquid phase. So, and then your liquid phase will have high concentration, right, in there. So because liquid phase is determined at this point, so you have very concentration jump at the interface, and this will decay away, right? And this diffusion normally decays by diffusion process, and it's either through solid or through liquid phase in there. But in most cases, we probably ignore the solid diffusion because solid diffusion normally ds is about 1,000 times lower than dl. So essentially, this diffusion is liquid controls one, and then you have this kind of exponential decay of concentration profile. So and then this will give you kind of a melting temperature variation like that. This curve, this we call a local liquidus temperature profile. So you have this one, and then you can apply different thermal gradient. Look at the TG1, TG2. If TG2 condition, and then any materials forms or solidified will be melted. And if TG1 condition, you got this kind of, we call it constitution undercooled area, and this area where you can form new grains, or if new grain forms, and it can grow. So this is a concept called constitution undercooling, and this is mainly what be the most important concept for this solute dendritic modeling, right? So you can apply different thermal gradient, and then to avoid this kind of columnar to equation or promote one. For example, in direction solidification, if we want to grow single crystals, and you normally will use high thermal gradient, low gross velocity, essentially TG2 like that, and you would not allow any grain to form ahead of solidification front. But if you want to promote this one, for example, in continuous casting process or even welding process, you can minimize it, and by introducing this kind of heterogeneous solidification, either by alloy design or you can by process optimization, right? So that's the theory, and now we have a computer program to simulate the whole process that I explained to you earlier, right? Now we try to do the calculations, right? And we use kind of stochastic modeling method, which probably can use phase field, and we use cafe method to do it. Essentially, we solve what we call the temperature against time and against spatial location with concentration profile, and then those two are globally solved. And then you will also solve this solidification front, and essentially to determine the solidification rate, and then move the interface around. So that's essentially what it's about. We call solidification theory. So if you look in a bit more detail of it, and then this will be in the center, this will be growing cells. So those growing cells is controlled by this equation. Essentially, this is diffusion liquid, and then this would be a solid partitioning at the solidification front of it. So this is, you apply this game to all computation domain, and it depends on if you have large domain, it take a longer time, right? Quickly show this movie. And this is a movie we try to use, actually is aluminum copper as example. This can be used to interpret other systems. A different color represents different concentration level. The green one looks at the concentration is a lower concentration, and the red color represents higher solid concentration. You can see how the concentration evolves and during solidification process. And then you will also see kind of a chromolar grain transform to equal-X grain. But in this process, we try to mimic a welding process and to reduce the thermal gradient. When you reduce the thermal gradient, you have you increase the possibility of form new grains ahead of this grain front. So you can simulate the chromolar to equal-X transitions. So this is a tool we actually, when I work with Peter, we use this code for a very long time. And then it's still available, and if anyone want to use it, I welcome to use it. Right. This supposed to 3D movie, but does not show you on this app PC. Yeah, and you can do 3D analysis, look into our comparison between 2D and 3D analysis. Essentially, look into solid profiles and look into it. So you can have a longitudinal view of what happens inside the crystals. And then also look into other effects such as undercooling, pooling velocity, essentially thermal gradient velocity. And another thing you look into primary spacing, essentially is original structure, how the original structure will affect actually the weld pool growth rate. Right. In the end, you can do the similar things as analytical modeling doing, and by showing this kind of CET maps over there. And this would be equal-X grains, and this will be chromolar grains, and then give you indication if you want where you are in the processing map, right? So solidification structure modeling, where the probably can say those either chromolar or equal-X grain can be simulated, and then to visualize the solidification in structure in this during welding, and also we said a complex solid interaction can be observed in the simulation, and which will be quite important to look into not only a structure model, now we look into effect microsegregation, how diffusion will occur, and this all can be investigated. And now we can use this as a tool to examine effect of processing on the grain structure evolution. Right. Good. Okay. That's all I prepared for you. Now I'm quite happy to answer your questions.
Thank you very much, Professor. Please ask the question and switch on your camera so he knows who's speaking, so he can address directly. Anna, please go ahead.
I'm just going to turn all my electronics off. So, hello, thank you very much. That was a great talk. I have one question for you. You talk about the importance of surface tension on the weld pool, obviously the depth, the width. Have you looked at the use of different types of flux, or is flux something that you covered in your modelling at all?
This is a very important question, and I didn't explain clearly what we did in reality, and we used different grade of steels to act on it. But in practice, you should really look into a surface, modify the slack systems to do it. But we try to mimic what happens. Yes. So this is the important question. Yeah. We said this using surface reactive element, not only sulfur, oxygen also can play a role, and also looking at other alloy elements. That would be more probably practical, applying this technology. Yeah, but in those movies, what I showed you, and we use steel with different concentration of sulfur. Yeah.
Thank you.
It's a shortcut.
Lucas, go ahead.
Uh, Hi, Hong. This is Prakash. I hope you remember me. I met you once in Leicester. I worked with Peter, X-ray imaging. It's a very good talk. I have one quick question about the experimental setup you used in situ arc welding as well as taking radiographs. So what is the sample thickness through which the X-rays passed in your radiography setup?
Right, sample thickness is about the diameter of sample is 10 millimeters.
Yeah, but
Yeah.
when you are doing the welding, it is placed on something or up to what thickness the welding was carried out?
Right. Okay. So what we should use kind of spot welding, right? You may have say 10 in diameters in this kind of it's a bar sitting in there, and then well actually if you use TIG welding and you met the proper lawfully met, will met probably 8 millimeters. Probably you have a couple of millimeters to contain the liquid inside. Yes.
Yeah. So the bottom is still the solid. So there is only a tiny bit of area.
Yeah, we see on the copper plate. Yeah, if you really want to, we have quite an interesting one. This is spot welding. We also do the translate kind of welding. That's more practical, look into additive manufacturing process. But difficulty is it's so difficult to analyze the data. We still have probably how many terabytes data we have not touched it yet. And then we worked in the group in the looking to in TU Delft. They said they're one leading group in this kind of a CFD modeling of the flow. And then when we present this to them, this is too complicated. But if any of you are interested, I'm quite happy to share those data with you and to look how to analyze. That will be more important. Look into actually arc welding process. Look into welding for automobile. Normally, sport welding is not very popular method. Anyway, yeah.
Okay, thank you.
Translation of the plate. That was very interesting. I'm very, very happy if anyone have interest in doing this. I'm still happy to share those data with you. Yeah.
Thanks.
And anyone? Oh, Claire, go ahead.
Yes, I'd like to take the opportunity to ask a question as well. I find it really interesting to see the macroscopic flow, and I think it's really quite fascinating because, as you say, it's the first time you can really get a feel for what's going on within a weld pool. And I was wondering about the coupling between the macroscopic flow and the microstructural modeling, where you've got your transition points, and how easy it is to couple those two things together, and particularly how it then might influence the proportion of columnar growth to then the equiax growth. And one of the reasons I asked the question is really whether we can do anything to modify that to give us better properties. For example, using electromagnetic stirring during the solidification part for welding, because that's certainly something that we used in continuous casting.
Okay, that's a very challenging question. Okay, because some say I cannot do it right now, but we think about it this way. But currently, those flow modeling is at a kind of a little bit larger scale, look at the probably micrometer scale. Many are still experimental methods, and we have very simplified 2D CFD modeling to mimic or to try to mimic what happened inside the flow. But in solidification modeling, currently it's purely a solute-driven process. But we think flow will definitely play a role. I think our assumption made in our simulation, we said servo profile probably is pretty straightforward, and flow is something we want to introduce into it, but we in the end we just simplified into diffusion control flow. We have not introduced convection into it, and the argument is a convection will affect macro scale phenomena. Those diffusion layers always exist. As you said, if you look at diffusion profile, you introduce electromagnetic stirring, and then you will cut the tail of this solid decay, the curve. You will cut the tail of it, but you probably won't be able to get into the influence on this at the interface. But at the interface is controlled by thermodynamics. and we still believe our welding process, the solidification is controlled still by the thermodynamic equilibrium states. Right. So there are areas we need to look into it. First of all, look to someone who is very good at CFD modeling to help us. My background on solidification modeling, look into more on theoretic type of solve the diffusion type things. And if we can have someone which is good at 3D micrometer kind of flow phenomena, and then we can work together to plug our solidification structure into it. I can move the interface or someone to help me to solve the flow, and essentially see how this kind of convection to interference interact with kind of solid diffusion, and very close to the interface, looking to probably less than 50 micrometer scale. Yeah.
Okay.
This is something
it is very interesting. I know that there's been quite a bit of work that's been done for continuous casting, which is closer to what I understand a bit more. And in terms of the flow modelling, I think it's something that Michael Auinger, who unfortunately wasn't able to join the talk today, he's done a little bit of the macro modelling for flow and how it influences dendritic growth directions, for example. So here, perhaps we could remember to flag up to Michael to watch through, and maybe it'd be something that Michael would like to talk to you about further, Hong.
Yeah, exactly. Yeah, look forward to it. Yeah,
good.
It's something I cannot do it myself, but I'd like to work with someone else to know.
Super. Thank you very much.
The interaction between the convection flow and the diffusion layer ahead of solidification front will be a very good topic, and this affects many other things. We look into actually working with Rosler, look into with orientation control, look into other defects or macro segregation. You said a continuous casting process. Definitely how to link this kind of macro segregation with macro segregation. Definitely they are linked, but we do not have a very clear or accurate way to describe them yet. Yeah.
Joseph, please go ahead. Joseph.
Hi, Hong. Thank you for your great talk. I have a simple question. Is you demonstrated the software can control the depth of the pool, the software content. So any other elements can achieve the similar effect, or what elements actually use in industry practice to control the depth of the pool in terms of Marangoni flow?
I think industry-wide, probably sulfur is one of the most practical elements, surface active elements to it. Other elements such as oxygen also has a strong control of it. And since we're really looking into it, we can look at other alloying elements we can use. This is something we're searching for it, but I do not have answer yet. Yeah.
Okay, thank you.
Thank you. Good.
Anand, please. Anand?
Anand, you're on mute.
Oh, sorry.
Okay, it's okay now.
Yeah, thanks for the beautiful talk. I have a very basic question about the fluid flow. You calculate the average velocity of the fluid particles and the maximum velocity of fluid particles. Have you calculated the effect of welding process parameters on the fluid velocity, like welding speed or the net heat input to the workpiece?
But in those experiments, and then we just calculate what we observed. So it's spot welding, and then it's pretty quick. Each experiment probably takes about a few minutes time, but we did not look into processing wise to affect the flow. But this things could be looking into it, and we still have this rig available. And if you want to use it, we can work together to do further experiments on this one.
Okay.
Yeah.
Thank you.
Is any more question from anyone? I think we are exactly on the time actually too. So thank you very much, Professor, once again. I have one question through the email. So thank you very much. Thank you. So I'll stop recording now, and
I'll echo Hiran's